Welcome. We have been looking at algorithms and looking at performance of randomized versus deterministic and then quantum versus randomized, right? And we have seen at least one algorithm where quantum does better than randomized. And this algorithm was called, what is this algorithm? Bernstein-Vazirani algorithm, right? And we saw that some problem which we can just solve in one query in quantum takes lot more k queries in the quantum setting, in the randomized setting, right? So first, let me once again clarify the problem. What is the problem? You are given a function as an input. Okay, f from 0, 1 to the k to 0, 1. Other way to think about it is, you have a n length string where n is equal to 2 to the power k. Makes sense? If your input is a function, that is basically saying your input is the truth table. Value of the function at each of the input, this is your input. Correct? And since the output is a 0, 1 thing, I can capture it by a bit. So I can think of my input as a function from 0 to the k to 0, 1, or I can just take the truth table of this function, which is of size n. So I can say that I have some n bits as my input. Does that make sense? Good. Now, I am given that this function is of a specific form. It's a promise problem. It says that these x1 to xn are related. How are they related? F of x is summation ai xi mod 2. Okay. So since I am writing this x and this there, let me just change it to y1, y2. Okay, so x is a string of size k, y is a string of size n. Y is the truth table, x is an input of this function, right? And how do I get yi? Yi has a binary representation. I just multiply summation aj xj or aj ij. That's okay. The function definition is quite clear, right? This we have done before. Now, the question is, what is a? Given such function or given ability to query these yi's, the question is, what is a? Okay, and randomly you can show that just one query can give you at most 1 bit of information about a. How big is a? What is the size of a? K, right? Because x is size k. If you are taking a dot product between these vectors, a has to have the same size as x. So a is of size k. That means to figure out a, I need order of k many queries from this black box. Correct? On the other hand, quantumly I can do it just in one query. Right? And the idea was very simple. I will just write this as tilde. I will cancel h. I will just write the first state. 1 will remain as it is. Sorry. The header mode will make an equal superposition over all inputs. That is fine. N is to the power k. Correct? Now I apply the function Since my b is 1, again, I should ideally write the entire state. I am writing just this state because I understand how this oracle works. Right? Ideally, in any quantum algorithm, when you look at the action of the circuit, you should write all the qubits. But here I understand what one is doing. There's a simple state. That's why I am being lazy. So what do I get here? What phase do I get with OF? What does OF do? -1 to the f of x, right? This is what my oracle does. It puts a phase of -1 to the power f of x. Correct? It is computing function in the phase. The other oracle would do x comma f of x if b was 0. This one will put it in the phase. So there was multiply by 1. Ideally, let's just keep writing all the states. Okay. Now, what do I know about fx? What is fx? What is fx? Written on the board. AIXI, right? Correct? Now, I apply Hadamard on it. Okay? So, one way you saw what I did was, I said this is -1 summation AIXI, and I took the phase -1 to the AIXI with xi bit and then decomposed it as a tensor product. That's what I did last time. Today I am going to do it slightly differently. Okay? Now, my question is, you take a state x, you apply Hadamard, again, J is going over all possible states. This is an orthonormal basis. So, after the action of H tensor K, X will look like something like this. It is some linear combination. What is this? What should come in the blank? -1 to the? Yes. -1 to the x dot j. And this is not hard to see. This was even an exercise in your notes. Why is it true? Okay, first, what is the simplest case? X is equal to 0, right? So clearly, what happens at x equal to 0 if I apply Hadamard? What do I get? On 0 state, if I apply Hadamard, I get for 1 qubit. For k qubits, equal superposition, right? We have done this. Here it is, right? So then I should get 1. If x is 0, I will get 1. 0 dot j is always 0, whatever be j. Correct? So this is definitely true for x equal to 0. Correct? Now, what happens? Suppose x is x1, x2, xn. Correct? Now, correct? like Hadamard, if x1 is 0, it will go to plus. If x1 is 1, it will go to minus. This we know about Hadamard, right? So it looks like this state. Correct? So I can say something like this, right? And now let's say I want to ask the coefficient of 1, 1, 0. Correct? That's what I'm asking here. My j is given to you. Let's say my j is 1, 1, 0. What is the coefficient? Minus 1. Why is it minus 1? Because I get a minus 1 from here. So when will I get a minus 1? If xi is 0, then this is a plus state. I will not get a minus 1. If xi is 0, I will get a plus state. I will not get a minus here. So first thing is xi should be 1. Second thing is I will get a minus if this state was 1. That means ji was 1. So I am getting a phase of minus 1 only if both xi and ji are 1 from the ith position. Let us look at the first position. Right? What determines whether when I open this thing up, whether I get a phase of plus 1 or minus 1 here? Okay, clearly this place will give me minus 1. First, it should be minus. That means x1 should be 1. Right? Second thing, I should not be taking this part in the output. I should be taking this part. I'm taking this part. That means J1 is 1. This is J1, right? When I expand this out, this will go to J1. So I will get a phase of minus 1 only from the ith branch, right? That means from ith branch, I am getting xi as the phase. What is the total phase I am getting? Summation I xij. That's why you got x dot j here. So this is just simple math analysis, probably even below high school. How we are opening the brackets. There is no quantum here. Once you know that, we have this kind of expression. So now this thing is and I am asking, what will you get here? This is what I am asking, right? So let's say even if I forget this, let's say just 3 qubits, and I ask, there will be 8 states here. What kind of minus 1 to the power? What phase I am getting, right? So for 0, 0, 0, I will never get a phase because 0, 0, 0. Even if this was minus, I will never get a phase, right? So I am collecting minuses only when my ji bit is 0 as well as xi is 0. If xi is not 0, then I get a plus state. There is no minus sign. If xi is 0, then I get plus state. If x2 is 0, then I get a plus state. Then there is no way I can get a minus sign from that coordinate. Right? I only get a sign when xi is 1. So xi has to be 1, and even there, if I pick up this part, there is no phase. So I have to pick this part. That means gi is 1. So then, what is the phase because of this term? x1 j1. What is the phase because of this one? x2 j2. What is the phase because of this one? xk jk. What is the total phase? Summation xi ji. This is the total phase I am collecting, which I have written here. Sorry, we will have double sum, right? So there will be a sum because of x, there will be a sum because of g, right? And because of x, I will get this x, right? This, how much it will contribute for g? It will contribute 1 by root n. So this 1 by root n became 1 by n. And this directly comes and it will also contribute x dot g. Okay. So j will have contribution from x1, x, different x's. There are to the power k x's. Each of the x will contribute as a phase for g. What phase? This phase. J is again a basis of c to the power k or c to the power n. You are applying Hadamard. You have an orthonormal basis on c to the power n. You are applying Hadamard. You are getting another basis. The same. I just don't want to write it in terms of x. Just want a different variable name. So I've called it j. But it's basically j takes values from cat 1, cat 2 up to cat to the power k. Yes, sure. Exactly. J are all k-bit strings. Because that's our basis, right? That's where Hadamard will take us. C to the power k, k qubits to k qubits, right? So this is, J is a basis for k qubits. Like these I am denoting by J. This is the first J, this is the second J, there are 8 Js. Okay? But X is also in the same space. X is also k-bit strings, but X denotes semantically the input. So I have said that my c to the power n has n basis states, each of them correspond to one input each. Right? So X and J are the same thing syntactically. They are k-bit strings. But their purpose in my algorithm is different. X denotes the input, J is in some sense the output here. That's why I'm denoting by them, otherwise it will be a confusing.
J is the output.
Not the output, I mean, sorry, after Hadamard, you can denote it by Y if you like. If
A dot x minus A dot x would be the output.
No, A dot x is with the x.
Minus 1 to A dot x plus x dot k. Yeah.
So, see, forget about other things. This is the Hadamard on this state. Minus 1 to the power A dot x is written as it is. The phase is as it is. What I have done is, for x, I have written the Hadamard. I have written what happens under the Hadamard. Right? And if you don't like J, you can change it to Y. But basically, it's a basis of C to the power N. my header mode will take it to another state in c to the power n, right? So I have to write it in terms of orthonormal basis. So that basis I have called J. Questions? Okay, so this fundamental fact about header mode is very, very important. How header mode ends, right? And now, if I exchange the summation, I will get all of the phases on G, right? Each of the X, when applied to header mode, will give some phase for the J, right? So phase of J would be summation over X correct? This is the total phase on J. Like if you look at this, or even if you look at this state, every output state J will collect a phase from X. 0, 0, 0 will give a phase of 1. 0, 0, 1 will give a different phase on J. 0, 0, 0, 1, 0 will give a different phase on J. So all of those I will collect. And this is written here. And why am I doing this? Because this is exactly the square, the absolute square of this is the probability that I measure J. This is what I'm doing. I'm going to measure here. Right? So obviously, I want to understand my state here. This state is where? This is a state of k qubits. And how do we understand the state of k qubits? We write it in this basis of 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And I need each of the amplitudes. This is what I am calculating. On 0, 0, 0, there will be a phase because of x being 0, 0, 0, x being 0, 0, 1, x being 0, 1, 0, and that will be the simple case. Then J being 0, 1, 0 will collect phase because of all possible n choices of x. So, okay, this is my input, c to the power k. They have some phase already with that we will attach, right? But then what is happening? When I apply header mode to this, it spreads that phase to all of the states. What about this? Spreads this phase to each of the k things, and each of these are labeled with x dot j. 1 by root n equal amplitude, but with a phase of -1 to the x dot j. So now this thing gets a phase from here, 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 from all the x's. From all the x's, it gets a phase of -1 to the a dot x, which was already there, plus x dot j because of the header mode. Like x is different here, x is 0, 0, 0 here, x is 0, 0, 1 here. So I can say with each of these states, there was already a phase. Header mode gives an extra phase. Okay, and yeah, by the way, there is a 1 by root 2k, 1 by root 2. Right, that normalization you can always calculate depending on what the states are. The phase is the important quantity. Questions? So even though this might look like in formulas a complicated thing, but this is what we have to do to understand this circuit. What we have to do is write up this state in full generality. We know this full state is going to be linear combination of 0, 0, 0, 0, 0, 1, 0, 1, 0, so on and so forth. Each of them is going to have an amplitude. Amplitude has a magnitude and a phase. So then, I'm just trying to understand this way. Okay, and each of these states, 0, 1, 0, gets something from here. What does it get? Minus 1 to the a dot 0, 0, 0, because that was already there, and then minus 1 to the x dot j because I am applying Hadamard. Similarly, it gets something from here. Similarly, it gets something from here. So I keep adding it for all x's. X goes from all k qubit, all k-bit strings, all inputs, right? Now, I want to understand what this number is. I can write a plus j. It doesn't matter. Everything is happening mod 2. Right? So a XOR j, a plus j, however you want to write. Right? I can take x common out. You can write it as xi, ji, ai, ji, and you can see it will become gi plus ai. Right? Now is an interesting question. What is this expression? Right? It will obviously depend on what this quantity is. What happens then? Wait, you can do it, I know, so wait. What happens on this? If a XOR j is all zeros, then 0, 0, 0 times x is 0. Minus 1 to the 0 is? This is n. 1 added n times, no? X is a k-bit string. You are adding 1 n times. So you get n. Okay. So then 1 by n, so the phase on, and when will this be 0? When j is equal to a. When will a XOR j be 0? When j is equal to a. So the phase on a is 1. What is the phase if a XOR j is not 0? You want to calculate? Do you need to calculate? No, why not? It's a unit vector, right? What you should get in the end is a unit vector. You have already got a vector which has the entire amplitude. So everything else has to be 0. So there, the phase will be 0. But it is actually instructive to see what happens. Okay, and this I will let you figure out. If this quantity has at least a single 1, then for half the x's, this will give 0, for half the x's it will give 1. Okay, so minus 1 plus 1, minus 1 plus 1, they will cancel out. And this is not surprising, okay? What happens? Suppose this is my a XOR j. Okay. Now let's say it has this as 1. Now look at x when this is 0 and when this is 1. So this with a XOR j and this with a XOR j will have different parity. Whatever be here, if all these coordinates are the same in x and y, because they are different at this and there is a 1 here, that means there is a difference of 1. Everything else will give the same thing. This coordinate will give 0, this coordinate will give 1. So they will have a parity difference. So these two here will cancel out. One of them will give a phase of -1, other will give a phase of 1. And they will cancel out. Other way to say it is, for half of the x's, there will be a -1 term here. For half of the x's, there will be a 1 term here. Entire thing. So that's why you get a 0. This is a very standard thing in standard computer science. When you play with bits, this kind of phenomena is used a lot in communication complexity and everywhere. I have told you once, if it is not clear, I would be happy to explain it after the class. Okay, but let's move on. The important point was that all my phase gets collected on A. Okay. So this was another interpretation of Bernstein-Vazirani. Right? Great. So by the time I erase it, you have time to ask any more questions. I should have kept this. Okay, so when you have a k qubits, you want to analyze that H tensored k. There are multiple ways. One I told you last class, where you look at the phase collected everywhere, you split it as a tensor product of states. But that we got lucky. In the worst case, you will have to just calculate it brute force. So you will have to say, okay, what is the phase coming on 001? Calculate from all possible ways. This is what we did here. Okay, and what we saw was that the in the randomized case, I haven't given a proof, but I have told you that since any random query can give you at most one bit of information about A, and A is k bits, I will need around omega k queries. So at least I will need k queries or constant times k queries in the randomized model. Quantumly, I have done it just with 1. You have the circuit right here. I am using OF only once. Right? Seems brilliant. 1 versus k. Right? But what is the input size of this problem? What is the input here? We have talked about it. What is the input for this problem? Function f. Right? How did we specify the function? As a truth table. Right? So what are my input? My inputs are y1, y2 up to yn. I have to specify these function values, then only my function is specified completely, right? So that's why my input is size n. Okay, so this gap is exponential. It seems nice, but if I write it as log n, then someone can say, oh, the number of queries I need quantumly are see, what do we want to show? That QF is smaller than square root RF or RF to the power something, right? So then, yes, it would have been, if just the relationship was direct, there was no additive factor, then clearly no power of quantum can compare with random, right? You raise 1 to whatever power, it will still be smaller than random. But then, since here, if I'm allowed to put an additive factor in terms of input size, then now this is not very, this does not contradict this statement. Correct? But if this was true for QF and RF, then this will not be very, very impressive. So what I'm trying to say, this is a general phenomena, these separations, there I want these because if you just, you say that you have a n list input, if you can anyway do it in 1 or log n, then your input anyway will be reading n length input or something. So these speedups are not impressive if they are very, very, these numbers are very, very small in terms of the input size. What I'm saying is that in all of these, I haven't talked about how I will do OF, right? And since OF has size n, what will happen is, as soon as I start putting complexity of OF, this will become log n times some factor of n to the c, and 1 times n to the power c. Suppose I have some actual implementation of Oracle, right? The Oracle, since given the Oracle is something which is applied on n things, it might have a big complexity itself. But then this is not a great speed up, right? So there are multiple ways to understand why we would like a separation where these complexities are comparable to input size. And this we will achieve using sign.